morning, everybody. Welcome to the Geoprobe webinar on an introduction to the low-level MIP system. My name is Tom Christy. I'm the Vice President at Geoprobe Systems and Director of the Direct Image Working Group in Geoprobe Systems. And I'm here with Dan Pipp, Chemist in the DI group. We're going to split tasks on making this presentation for you today. The great George Washington Carver used to say that everything he knew was available to you for the price of a postage stamp, and we're going to try to make it even better. It's free, everything we know about this topic. You know, you're busy people. We're going to try and make it through this in an hour and hopefully give you some very good material. Low-level MIP, an enhancement to the MIP system that gives us lower detection limits and better signal to noise. So we have greater confidence in finding contaminants in the subsurface. Our agenda for the webinar today, I'll be going over the low-level MIP concept. We'll trace our thought pattern as we developed the low-level MIP system. Then Dan's going to go through basic operation of the low-level MIP, how it looks when you actually operate it in the field. And then he's going to go over field data examples. And he'll actually do those in the DI viewer, showing you comparisons of standard MIP logs along with low-level MIP logs. And finally, then actual examples of low-level MIP logs and sample data. At the end, hopefully, we'll have time for a few questions and answers, and we'll also give you instructions at the end on how you can get a certificate of completion for this one-hour webinar. Here's some basic concepts. We've got to go over this a couple basic concepts. I know the attendees out there have a wide range of experience with MIP. Some of you have done hundreds and hundreds of logs in the field or reviewed many, many logs. Some of you are very much beginners to MIP work for detecting volatiles in the subsurface. This first concept, though, is the response test, and it's a concept we're going to use a number of times in this webinar in order to compare low-level MIP work with standard MIP work. The response test is when we expose an MIP probe, typically to an aqueous solution of containing a volatile contaminant, and our typical exposure time is 45 seconds. So on the graph we see here data, detector data, signal, XSD in this case for chlorinated specifics with time. Response tests are signal with time. And in this case, we exposed the MIP probe for 45 seconds. And then we see here somewhere around 65 to 70 seconds, we began getting signal coming over on the detector. And it rises to a peak. And we often refer to the peak value that we got from a response test. That's what we often compare. It's what we often compare in discussing low-level compared to standard MIP. And you can see here for a 45-second exposure, the peak is broader than that. In fact, it's probably close to 90 seconds in width for a 500 part per billion TCE response test. The reason we use this response test is that it tests our entire MIP system. We always have to have, if we're going to collect data with a device, we have to have a QA test. And this is a very reliable QA test. When we use it because it is very much like what happens in soil when we leave a probe at a depth, using standard MIP in this case. We leave a probe typically for about 45 seconds at a depth, and we get a response that looks very much like this response test in aqueous fluid. The second concept is the log itself. Now we've gone from The response test, which is signal with time, to the log itself, which is signal with depth. And what this is a transformation of the response test. We're going to take this and convert it to a discrete depth. So that response test would represent one of the peaks that you'd see here. When we stop the probe at a discrete depth, we give it time, we get signal over, and then we transform or assign that signal to a discrete depth. So the red line here is an MIP log, in this case a standard MIP log. In the case I'm showing you here, it's been overlaid with sample data. You can find this example on our website for MIHPT data. And it's a good log. It was taken in an area of fine-grained soil, and so we have done soil sampling, so a core in here, and divided mini cores, which we then had analyzed, and you can see that the MIP log does a very good job, in this case, of describing the distribution of volatile contaminants in the subsurface. This is total VOCs we have. You can see that everything here on this log, everything in the samples was less than 500 micrograms per kilogram in the soil, and we had good signal for that with the MIP. But we have other cases, like this one, where signal's not as robust as we would like. This is a case run with an MIHPT probe. You can see on the left side is an HPT log that accompanies the MIP. It's made simultaneously. This zone here that I'm pointing to with my cursor is a zone of very low MIP pressure above the hydrostatic, and that indicates in this zone here we have coarse-grained sediments, sands and gravels. We begin getting MIP signal here in this zone. It's not exactly robust signal, and we can see that we've done groundwater sampling here, and we have nearly 4 part per million down to 1.5 part per million in these areas. It's not exactly the signal we'd like to see. We'd like to see more signal out of there, more robust signal. Even when we rescale it, there's more than I showed you in the last slide. But even when we rescale it, it's not exactly satisfying, and we don't have a lot of signal left there to take us down to lower concentrations in these coarse-grained sediments. When we get into fines below that, of course, we have more signal. But looking at this log, we started with the problem and said, how do we get more signal out of an MIP system? Well, there's several ways to do that. One of them that we've known about for some time is reflected here in this graph. This is where we've done response tests, like I showed you in the earlier slide. We've done response tests at many different MIP flows. Most people in the field are probably using flow rates down in this neighborhood, around 40 mill a minute. And here's the response at that flow rate. We know that as we decrease the flow, we can increase our response. In fact, we can double it if we cut the flow rate in about half. The trade-off there is that it takes longer to get signal up to the contaminants up to our detectors. If we even get down below 10 mill a minute, we see that eventually it even falls off. It's taking so long to get that contaminant up to the detectors that dispersion in the trunk line becomes very significant. But the thought process started, well, what if we slowed the flow down? And this was really our breakthrough. What if we slowed it down here and got a better response, and then we switched our flow and sped it up to take the sample to the detectors very quickly? That was our breakthrough question. Well, we took that question and extrapolated it and said, wow, not only could we do that, what if we just stopped it for some period of time. Look what we could do up here if we extrapolated that curve. We could get this at a stopped flow and then speed it back up. And that's how the idea developed. Let's stop the flow behind the membrane. There's a headspace directly behind that MIP membrane. It's a very small headspace, less than half of a milliliter of space behind that membrane. So let's stop flow, allow the concentration to build behind the membrane, and then we'll start flow again and push that contaminant pulse quickly up to the detectors. So again, we're going to take advantage of stop flow here, accumulate a concentration, becoming more like a headspace test behind the membrane, and then we'll start flow again and push those contaminants quickly up to the detectors. Good concept. And we went out and just tried it in the lab as a feasibility test, and quickly we see these type of results. So again, what I'm showing you on the left here is a response test on standard MIP, and you can see the broad peak that we're getting and the response. Whereas at the same concentration, if I use this stop flow, start flow method, I can get a very narrow band, okay, that's in sharp contrast to my baseline noise. And I get a magnitude on the peak that's about an order of magnitude greater than my standard response test. We did that in a feasibility test, and we said, wow, we're onto something here. This is not only a much higher magnitude on my signal, but it's much easier to separate from baseline noise. Those are the ingredients we all want in a detection system. So we said we're Geoprobe. Let's design a flow circuit to do this function. One of the things we have to do, since we're starting and stopping flow, is we have to provide a steady gas stream to the detectors. Detectors don't like to have their flow stopped and started. So we put in a sampling valve. Those of you that are well-versed in gas chromatography will recognize the gas sampling valve and sample loop that we used in our system. From that, we built that into a controller, and this is the piece of equipment that you would need in order to do low-level MIP. That, of course, with the accompanying control software that is now built into the MIP acquisition software. Dan's going to go through that in a minute. I don't know where that sound's coming from. I don't know, somebody with a radio nearby or something. So what we do is we put the low-level MIP controller. We're good? Okay. We put the low-level MIP controller in a standard MIP system. And besides adding this low-level controller, the only other part that we have to add is this detector supply gas. Okay. You have to come up with a standard 20 milliminute gas stream that comes over into this low-level MIP controller. So here's the basics. When we stop the flow at depth, we begin the low-level cycle. Flow behind the membrane stops, and the sample concentration builds. Flow is restored, and the sample is swept to the transfer loop. And now a handoff takes place between the MIP system, the MIP probe and trunk line, hands off through the loop to the detectors. So detector flow takes over, and it sweeps the sample from the loop to the detectors. And now our detectors never receive flow directly from the MIP probe or trunk line. They receive flow only, they receive sample only through the loop. And the result is this. On the left, this is a co-located log. On the left is a the standard MIP log. If we rescaled this, we would probably say, yeah, we've got signal here. But as we could say, it's marginal signal. It's difficult for us to separate signal from our baseline noise here and say with confidence, yes, we're in a contaminated zone here. But at the same location with a low level, we can get results like this. Say, yes, definitely, we've got good signal to noise. This is a contaminated zone. And we'll go through some actual examples of this with data here later during Dan's portion of the presentation. I'm going to hand off to Dan now, and he's going to go through an example of how the low-level MIP system actually cycles through and takes a sample. Dan, it's yours.
Okay, thank you for the history of the low-level system and how we got to this point. We do have, as Tom had mentioned, we have what just happened? Oh, okay. Sorry about that. We have our, on the screen here is a new control panel that we have added into the low-level acquisition software. So this is allowing us to control the cycling of the low-level system. And what we have here on the top portion is for the when we're actually logging the depth increments that we are going to fire the cycle of the low-level system. So on the top here, we have a length of increment. Every foot, we are going to trigger the cycling of this low-level system so long as we are within 0.2 plus or minus 0.2 feet. If you look here, when we begin the log from 0.8 to 1.2 feet, rate of push is 0 for 2 seconds. The cycle will begin if we're in that window. And that just automatically triggers when the probe is in that next window. Down here on this other section of the input screen is the parameters that Tom had talked about. Our no flow time is the time at which, the length of time we are going to be stopped and we're going to be collecting our sample at the membrane. We're shutting the flow off in the trunk line for 45 seconds. After the flow is restarted, in this particular example, the flow is restarted, and 33 seconds after that is when we are going to expect that sample to be located inside the sample loop. And the load loop time is the amount of time that we are going to be exposing the sample loop to the trunk line. So really only 10 seconds of time does the contents of the trunk line get sent over to the sample loop. The rest of the time, whatever's in the trunk line is just vented and we don't use it at all. So when this inject time is over, whatever is inside the sample loop will then be diverted over to the detectors. And then we can also see on this output screen where we are in the cycle, in this low-level cycle. And we're going to go through an example of that momentarily. For the example we're going to show you in a little bit, again, we are using 500 parts per billion of TCE in our standard. The detectors that we're going to be using are an XSD, the halogen-specific detector, PID, and FID. Our detector flow rates, again, the constant flow rate to the detectors is going to be about 20 mils a minute. And then downhole in the trunk line and in the probe, when our trunk line flow is going, we're going to be operating at approximately 60 mils a minute. We will shut the flow off for 45 seconds as we expose the membrane to the standard. And we have a longer trunk line. This is a 150-foot trunk line, so our inject time is 51 seconds. And that's, again, the time at which that we would expect that sample that had been collected at the probe to be in the sample loop. And we'll be exposing our sample loop to the trunk line for 10 seconds. As Tom had shown, this particular standard MIP response test with 500 parts per billion of TCE. Again, this is a very typical response test that we'd see in standard MIP. Continuous flow of 40 milliliters a minute, 45-second exposure, about 10,000 microvolts on the XSD for that concentration. That's a very common and reasonable, very good response that we would expect to see. Now we're going to go through the same concentration on the low-level method. Video here. We're going to start. We just started our response test. So we see our detectors coming across here. We started the low-level method, and we are now exposing our standard to the membrane and building up that concentration at the membrane. I'm going through our control panel for the low-level method and just going over those numbers that we had just talked about. Then we'll go back to the output screen and see that we are in the collect mode. You can see that by the red spot up there. And we can see that during this collection, our flow rates here, supply flow and return from the probe are at near zero, but we have a continuous flow of near 20 mils a minute to the detectors. So they're not seeing any variability in their baselines. Now, we just switched from collection to trunk line transport, so our flow has been restarted, and we are bringing that sample up the trunk line to the control box. In the last 10 seconds of this trunk line transport, we will switch over. The valve will switch, opening the sample loop up to the trunk line. And you're going to actually see some variability, a small dip in a couple of the detectors when that valve makes that switch. You may have just heard it right there. Valve will switch, and now trunk line gas is going to the sample loop. It'll switch back momentarily. There you go. And that, now what was in the sample loop is being sent over to the detectors. And we are injecting that to the GC. Over here, we've just gone to standby. So if we're advancing this in the ground and performing a log, at this point we could go down to our next sample depth. And here is the response coming from the sample loop. And we can see that nice sharp peak. So that is the PID and XSD responding to the TC. The FID is a little bit smaller, not as sensitive of a detector. But let's take a look at how those two compare. So once again, as Tom has shown earlier, we have the standard MIP response test down here, 10,000 microvolts approximately in the response, and the low-level response test there, approximately 100,000 microvolts, about a 10-time improvement in that signal. After those tests, I went back to take a look at what kind of a detection limit we could see with this particular system. And what I put onto the membrane and through the system was a blank. There's a 0 parts per billion there, and then 25 parts per billion, 50 parts per billion, and 100 parts per billion of TCE. And we see a nice uniform increase in response for those three concentrations, which we would hope to see, and we can be very confident that we'd be able to see those in the subsurface. And this is something that anybody who's hiring someone to do work, especially on lower level, lower concentration sites, I don't think it's unreasonable to ask an operator to supply current detector data, performance data, to see what the system is capable of doing. One thing I want to add here is just because an operator has a low-level controller, a low-level system, does not necessarily mean that they can see down to these concentrations well below 100 parts per billion. It is very much still dependent upon the contaminant, the site you're dealing with, but most importantly, the maintenance level of the detectors, of the detector system that they're operating. If it's not well maintained, they may not be able to see, achieve these kind of levels. The system will still improve what they can see. It's just a matter of determining what that level is that that particular system can do. So at this point, I'm going to switch over to the DI viewer, and we're going to take a look at some other logs here. And as Tom had mentioned, after we had done our response test in the lab, we then went out into the field and tried to take a look at how this would work in the subsurface. So I'm going to open up a standard MIP log now, and the DI viewer, again, is a free download off of our free software you can download from our website that we use to review, compare, and print all Geoprobe DI logs. I just opened this up in single log view, so we can look at any of the graph parameters that have been saved with one particular log. And there are different views that we can look at. This obviously is single log. We can look at overlay, where you can compare directly multiple logs, each graph of multiple logs to one another, as well as a cross-section view, where you can take one or two graphs and look at them as you, how they compare as you move across the site. So here is a standard MIP log, again on the edge of a hydrocarbon plume, where we see some signal here in the PID. This is a likely area where we would suspect to get some, that we'd have response. But you can see, as Tom had mentioned earlier, that the baseline here is not very pleasing. It's very difficult to discern whether or not we would have contaminant in this area outside of this spot right here. The XSD was just started right after the log was created, or after it was begun, and that's why we ramped up there, but we're not seeing much on that. What I'm going to do here is take this log, and I'm going to send this over to an overlay view. Same log in the overlay view. I'm going to just darken this up a little bit. So I'm going to go on a data point, right-click, go down to the series properties, and I'm going to increase our line thickness just to make that pop a little bit more. Now I'm going to, after we did this log on the edge of this plume, we switched over and performed a low-level log, and I'm going to add that here over this particular log. Again, I'm going to right-click on a data point and go to Series Properties and thicken that up. I'm actually going to change the color here to make this pop a little more. Go to a red, and I'm not sure why that happened, but we're going to, there we go, come back to the DI viewer. So you can see, first of all, first thing I want to mention here is in this overlay, we're going to look at the electrical connectivity. And we can see from the electrical connectivity on both of these logs, they basically trace one another. And that's an excellent example. Electrical connectivity, as well as HPT pressure, if you're doing MIHPT or HPT by itself, they are very reproducible when you're in very nearby locations, and it's a good indication that this is a replicate hole, just an offset within 1 meter apart. Again, we see where we suspected we had signal. We do. We have some very robust signal with the low-level system there. One thing I'm going to just note is it looks a little bit different. These peaks look a little stretched out, and I'm just going to say that This being one of the first handful of logs, low-level logs that we performed, we were learning some things, and one thing that I had done was set my trip time too long, and that stretched my peak out a little bit over the course of the foot advancement. So we know not to do that anymore, and the rest of the logs will show a very sharp peak, and operators that are using this know not to do that as well. I've learned from my mistake. So I'm going to clear this overlay, and we're going to go to a different location and look at, I'm going to open up the log that Tom had mentioned earlier. We're just going to look at I'm right-clicked on the HPT pressure graph. I'm going to remove that graph and just show our electrical connectivity and XSD response. What I want to show here, first of all, one of the newer features in the DI viewer is the ability to add custom data sets. Tom has shown those sample data that we had, and if you go to Tools, Custom Data Sets, you go to the log that you have open, and you can either add a new set of data that you have, whether it's water quality data or lab analytical data. Type in whatever the data type is, the units you want, add the depth and the data values that you want to show. Let's just take a quick look at this data that has been entered here, and we have the depth. In this case, we entered it in as feet. The meters self-populated based on that depth and foot level. Works the other way as well. And then we just entered in our concentration data over here on the right side. And that can also be inputted, copied from like an Excel spreadsheet as well. So once that's been entered into the log, you can go on one of the graphs. In this case, I'm going to go to the XSD and open up a secondary series and our XVOC concentration. And now we're plotting those data series along with our MIP graph. So we find that to be a very useful tool within this software. Now I'm going to add this. I'm going to send this over to a cross-section. I don't want to take a look at that. We're going to put the XSD on here. I got to right-click on this properties and make my points invisible. Okay. Now, this was performed a while ago when we were looking at our MIHBT and seeing how that combined system performed. When we were working on the low-level system, we went back and replicated the standard MIP log that was performed here with the MIHBT system. We replicated that, and here's our XSD response a few months later in standard MIP form. Now, and then we switched over after doing this particular log, and we did a low-level log, and these are all within 1 meter apart. Now, in this case, it looks like there's not a whole lot of difference, but first thing I want to do is I'm going to add in on a secondary series our concentration data. So we have that and can see that our highest responses are where we're seeing some added signal, both in the standard MIP and in the low level. But if we sync the graph scales so that they're all to the highest level, which in this case is the low level MIP method, we can see that we can really see the difference that the low level system is making here as far as the magnitude of responses that we're seeing. Another thing I want to just quickly show I'm going to right-click on the number 2 and set that as my maximum, and highlight down here. These responses that we got in the lab data are around 30 parts per billion of chlorinated VOCs in the soil. And it's very evident with the low-level system that we actually have impacts at that point. Obviously, where we're having it, upwards of 500 parts per billion, that's extremely evident on the low-level system. So with that, now I'm going to clear this one more time, and I'm going to go to, actually I'm going to open this next one up in overlay view. We're going to go to a different site. One last site I want to show some comparisons for you. And again, first we did a standard MIP log, and we can see here with the XSD, we have fairly marginal signal, maybe some impacts right in here in the 35 to 45 foot zone. And once we did that, we're going to add in the low-level log that we did at that location. And we see how, again, first of all, let me go to this. I can highlight on the end, I can highlight that on the EC, and I'm going to put a different value in there to make our scale settings a little more pleasing there. We must have contacted a wire or something, giving us a higher EC reading. But once again, like I mentioned a little bit earlier, in the overlay view, we can see in electrical conductivity and HPT pressure, those two logs that were performed, they mirror one another and give us very good confidence that we are in the same, that these are offset logs. Again, these are within 1 meter apart, so we can confirm by that we're in the same area. And especially when we come to the XSD here, we see very little response until we get down to about 35 feet. And we can see where we suspected we might have some response from the standard MIP log. The low-level log is showing very distinct impacts down there in that particular log. Now we're going to take a cross-section view of this area, of this particular site, and I can open up a number of these logs. There are 6 logs we're going to open up at the same time. I need to move this one. I right-clicked on the number 4 graph. I'm going to move that one left because that's the position it needs to be in. And we are looking at these 6 logs from the east side. This is south, moving north in that direction to the right of your screen. And we can see that there's not many impacts, a little bit at the bottom, maybe a little bit in this 35 to 45 foot zone in these first 3 logs, 1, 2, and 3. As we get to the 3 on the right, the impacts become a little bit more prevalent. And those are the 3 that I want to focus on now. So I'm going to right-click on the N3 log. I'm going to remove that one, remove 2, remove that one, and just focus on these. Once again, we're going to open up some user data. What we had done after we did the low-level logs here on this site, Wes McCall and I came back out and collected groundwater samples. This is a much more permeable area, coarser grain materials, and we went down with the HPT groundwater sampler and collected samples where we suspected to have no detections, non-detect locations, as well as higher responses. So we have a fairly good profile of these logs with the lab analytical data. And I'm going to show that right now. Here is our total chlorinated VOCs for these 3 logs. So we had samples down here that were non-detect. We went up higher. In this case, we were around 700 parts per billion, went back to non-detect, and it was higher down below. Where we collected samples where we could, there was a little bit of areas of some finer materials that would make it a little bit more difficult to collect samples with that particular tool. But these are the points at which we had collected groundwater samples in these locations. So one thing that is interesting, of course, we sent these into the lab. This is total VOCs here that we have plotted over these XSD graphs. What I'm going to do is we also had split those out into the individual components, and the makeup of the total of these chlorinated VOCs was 1,2-DCA, carbon tetrachloride, and chloroform. And we're going to take a look at each one of those individually, and it's pretty interesting in this cross-section. This is the 1,2-DCA, and over here on the N4 log, we have very low concentrations, just below 30, just below our water table. Higher concentrations, this is about 700 parts per billion, excuse me, 700 parts per billion, and 200 goes down to non-detect, basically, and it goes up a little higher in the lower portion of this particular log. On the other 2 logs, it really stays down pretty low in the lower portion of the responses after it's cleaned up. And as we move to carbon tetrachloride, the upper portion of the plume is non-detect, and the carbon tetrachloride is down below. And if we look at chloroform, likewise, there's very little of those impacts in the 35 to 40 foot zone, but most of those are down below in that lower impact zone. So we thought that was very interesting as we did these logs. So I guess a couple other things I just want to mention. That's about all I have for the DI viewer. A couple things I want to mention. I've shown logs run in standard MIP as well as low-level MIP, and I've talked about how we've switched between them. One thing I want to mention is it's very easy with an operator who has a low-level controller, if they run all their gas lines to that, it is literally only 2 lines and 1 union to change between these 2 methods. So literally it is less than a minute that it would take to change between running standard MIP and running low-level MIP. Another thing I just want to quickly mention is that when you're performing these logs, you're not going to run standard MIP and low-level MIP in the same log. In other words, run standard MIP until you maybe see some impacts and then switch over. You will run each method and each log type on its own. But if you don't get very many impacts, maybe just a little bit, you could switch over, move over a foot or 2, run a new log in low-level mode, and proceed that way. And this is definitely 2 different data sets. It's not something you'd want to likely model standard MIP logs and low-level MIP logs together in the same modeling program. So with that, I'm going to hand this back to Tom, and he will begin to wrap this up, and we'll begin to answer some questions.
And here we are at a summary. And while I'm going through this summary, Dan, you might have some questions. If anybody out there has a question on the low-level system, you could send those over to us now using the chat bar that should be available to you there. So if you use the chat bar, any question you might have on low-level now, Dan would be reading those while I go over the summary. We already have a few questions that have come in. Here's a summary. Low-level MIP is a way to enhance our detector responses by an order of magnitude over standard MIP, as well as giving us a much better signal-to-noise ratio, easier separation from baseline noise. It requires an FI-based MIP system because of the control software that we're using. It's built into the FI-based MIP acquisition. Successful logging with the low level is going to depend on loop timing. It has to be set up with the control parameters that Dan showed us. Of course, triggering can be set up to be automatic with depth. You move a foot or 30 centimeters, whatever you want. You can set it so it will automatically cycle when you stop at those target depths. You have to prove system operation with response testing. And as Dan said, anybody that says they can go out and do 50 part per billion or 100 part per billion work, we believe they ought to be able to demonstrate that with response testing that that's going to work. This low-level system is going to allow you to define plumes further and with better signal-to-noise ratios, greater confidence in that plume data. This expands your MIP system capability and increases your field time. Low-level MIP now becomes the most desirable way to cross-section or track those plumes. Now, a little bit of housekeeping here. Certificate of completion. After this webinar later today, you will receive an email asking if you would like to receive a certificate of completion. And if you do, all you have to do is reply to that webinar and use this webinar code. That tells us you actually made it to the end. You survived the low-level workshop and lived to tell about it. Or as an alternate, you could email to Joyce Smith at Geoprobe. She takes care of those for us. And there's Joyce's email address, smithj@geoprobe.com. Joyce, you're now famous. Okay. Yeah. Now a few questions that have come in. Dan.
Okay, we have a couple questions that have come in here, and one of them.
Can I give you one first?
Hey, sure. Yeah. You can give me one first.
Okay. How long do you have to stop flow? You know, all the examples you gave us, you were stopping flow for 45 seconds. That's kind of a standard response test time for us. But had you used alternate times, and how long would you have to stop it, stop flow on a low level?
That is, it's going to be somewhat dependent upon what kind of levels you want to achieve on your site. It is dependent upon the maintenance of the system that has kind of been mentioned earlier. But I have used different no flow times. Again, we used in these examples 45 seconds. I've used 30 seconds. I think we've even looked at stopping that flow for 20 seconds. And it would just be a matter of the operator, perhaps the consultant who's working with them, to determine whether or not they'd be able to achieve the kind of levels they want to see on their site.
So you've done it 35 seconds, and it's just a lower response.
Yeah. But, you're not gonna have as much that comes through and be collected in that volume of gas if you don't wait as long. So
okay.
The longer you wait, you're gonna have more come across and be built up into that gas.
Okay. Now tell us some of those questions you had over there.
A couple of these other ones that are coming in. One of them is that they heard that MIP systems do not respond well to DCE and vinyl chloride as well as PCE and TCE. I suspect that that particular question is because of the use of an electron capture detector, or ECD. That is very true for that particular detector. It's very dependent upon the number of chlorines on the molecule. So PC and TC have a very robust signal, although it doesn't take much for it to max out and not give you a good signal at all, and you're just saturated. We used, in these examples, an XSD detector, a halogen-specific detector, and that particular detector has a much better overall response, more level, for a wide variety of chlorinated compounds, vinyl chloride to PCE. There is some difference in how it responds, but not nearly as drastic as an ECD. The low-level system, yes, it still does improve on those compounds as well. As far as how long does it take, how much longer does it take to do a log when you're using this system? It will take a little bit longer. Again, we're stopping for a given period of time, and then once we start that flow, we have to wait until that contaminant gets uphole to the sample loop before we can advance to the next level. The longer the trunk line, the longer you're going to have to wait. It potentially, usually it probably wouldn't double. If you're normally waiting 45 seconds to a minute, it might be a minute and a half. So you might have like 1.5 times the length of time that it would take to do a log. So if it's a 60-minute log, it might be 90 minutes.
And that's actually on the logging side going down. Your movement between hole or you're pulling the rods is all the same time. I think on some of the logs we did, we figured 30 seconds more per foot, half a minute a foot more. So on a 60-foot hole, we were looking at an added half hour over standard MIP.
Another thing that was asked here, it is not limited to just the groundwater. Yes, it is. We can use this particular system as standard MIP as well, both in the vadose zone and in the groundwater. So it would be effective for a vapor plume, whether it has groundwater contamination or just soil contamination.
In fact, that first example you showed, Dan, of the hydrocarbons, when you went to the DI viewer and showed that hydrocarbon example, that would have been an unsaturated zone contaminant there. That was above the water table that we were resolving those hydrocarbons. So that would have been a vadose zone contaminant that we resolved with the low-level system.
Here's a very good question regarding like a mixed plume, longer trunk lines, mixed plume that may have a wide variety of trip times that come up. You definitely will need to take a look at the timing, and the operators will spend a fair amount of time just making sure their timing is correct, that the contaminant is in the sample loop. If there is a wide variety of contaminants in a location that you're trying to map, that they could separate and have different times to get to the controller, it potentially could be an issue. We could deal with that with longer sample loops, I suppose. But otherwise, it's potentially would have to pick one or the other as far as what you're trying to target and collect in the sample loop.
Dan, here's a good question. Someone wrote in and says, would operators require formal training with the low-level MIP? And that's affirmative. You have to be trained to operate that system. And for someone that's experienced with MIP, that's not onerous, but it would take you probably minimally a day of instruction, and then you don't want to go out and try and operate that on a paying project your first time. You want to have some backyard time, but a day of instruction can get that set up and operate. It does take training.
Here's the last one there.
With the flow stop, what causes the molecules to diffuse across the membrane? Same as in standard MIP, there's a concentration difference, and so that concentration difference is the pressure that drives those molecules across into the headspace behind that. Now, the longer we wait, of course, the lower the diffusion rate. Eventually, if we waited long enough, there would be as many molecules, theoretically, leaving and crossing back into the formation as there are coming across. How long that would take, I'm not sure. But that's why we put the contaminants into probably 1/100th of the volume that we do on standard MIP, but we come up with only 10 times the concentration. So its concentration gradient causes us to diffuse across that membrane. Well, I think that wraps it up for today. If you have any other questions, of course, you can email to Dan Pipp on this, is the best go-to guy for low-level MIP. Send us your questions, and we'll try and, even the ones we didn't get to here, we'll try and parse those out and get you some answers back on them. Thank you very much for attending, and again, you will have an email coming to you asking if you'd like that certificate of participation. Thanks very much, everybody, and get out there and use the low-level MIP.